Hello, Geography 231 students. How's everyone doing this evening or afternoon or morning? I wanted to quickly get through some announcements before I get going on this week's lecture. I finished reading everyone's papers and I finished providing feedback to everybody. So make sure you go on to turn it in. Then you just go back to the assignment location where you uploaded it and you should see your assignment. Or it could be that you go to your grades page. I'm actually not sure because I can't see it from the student side. You either go to grades and then select your paper. In either case, you should be able to find a link back to my comments, which are posted through Turn It In. So make sure that you review my comments because I provided hopefully what I hope is a lot of useful information to you in terms of data locations, methodology suggestions, probably a few little pointers for those whose hypotheses weren't quite crystallized yet. And so just make sure that you read through that feedback and hopefully you find it useful. And then this week and hopefully next week, your labs are relatively short, and so you should be able to use the additional time to work on your projects because this is week 10. We are already in the double digits, so week 10 is upon us. Next thing you know, we will be talking about preparing for final presentations. So just be aware of that. Keep in mind on the calendar. Don't let the end of the semester sneak up on you. It will be November 1st before you know it. November is a quick month with Veterans Day and then obviously the Thanksgiving holiday. And then really we're done after the first week of first week of December rather. So make sure you're taking advantage of all the time that you have. Talk to me if you have questions. I've had a lot of great conversations with students over the last few weeks in terms of preparing their proposals, but don't hesitate to reach out if you have any questions on how to, actually facilitate your project itself. I've been doing this for a little while, so I've got a few data sources in the old noggin. So yeah, talk to me. All right. So with that, oh yeah, and then I graded your midterms. Those were more recent, I believe. Midterms are graded, papers are graded, should be up to speed. All right, so week 10, patterns and clustering, part 2. This is more or less a continuation of what we talked about last week. So we're still going to be talking about patterns, spatial analysis and patterns, and then finding clusters. And we're going to work our way into hotspot analysis next week. Okay, so we're going to kind of stay on the same subject. All right, so patterns and clustering part 2, tutorial, we'll be analyzing patterns part 2, and that will be basically the same textbook that I used last week, which is that GIS Tutorials 2 Spatial Analysis Workbook. So this version right here, you don't have this, that's okay. I've uploaded the PDF to Canvas, just like I did last week, and like I will do next week as well. And so this week you're going to be finishing up this chapter 8. This time it'll be tutorials 8.3 and 8.4. There's not going to be a tutorial this week. The methods are the same that we employed last week in terms of using the GIS tutorials textbook tutorial, the tutorial for the tutorial, right? And then also the supplemental instructions. So I'm doing it the same way this week, where essentially the lab comes from a textbook that was designed for ArcMap, and obviously we're doing this on ArcGIS Pro, and so I've created sort of supplemental instructions to go along as a kind of like a supplement for the narrative there, just to translate it from the old software to the new software. So same as we did last week. So there's no reason for a tutorial. You'll be able to work your way through it just fine as long as you follow the instructions. If you have questions, as always, email, post on the discussion board. Upon completion of this lecture and lab, you should understand why and how to measure spatial patterns for feature values, why and how to identify spatial clusters, and you'll understand a few more GIS tools for finding spatial statistics. All right, so measuring the spatial pattern of feature values. Oops. All right, so in addition to measuring the patterns formed by the locations of features, patterns of attribute values associated with features may also be measured. So for example, patterns formed by the median house values or mortality rates. So we focus mostly on the spatial patterns of actual feature locations, but if we're talking about quantitative data or even qualitative data, we're also interested in not just where they're located, but what these values are. Because you might have, we'll say, think about a neighborhood. Of course, in like the suburbs, every house is basically on some lot with a 50-foot wide lot line or something like that. Every house is evenly distributed. So when it comes to spatial distribution, it's a pretty regular distribution. The homes don't really cluster the way that we look at like naturally occurring data. Homes, at least on the neighborhood level, every home is evenly distributed, and the spacing between them is more or less the same. But if you look at the median house values, or maybe the median income of the families who live in these homes, those actually tend to cluster, and you'll start to see spatial patterns. So if we're looking at a neighborhood, we'll say one is on the so-called right side of the tracks and another one is on the so-called wrong side of the tracks, right? So if you're looking at it from above, like in a helicopter, you might look down and everything more or less looks the same from above. All the homes are more or less evenly distributed. But if you're able to use GIS, you look down and you see that the homes on the right side of the tracks have a higher value. Perhaps the median household income is higher, and on the so-called wrong side of the tracks, maybe the values are a little bit lower, right? So in that case, it's still a spatial pattern, but it's a spatial pattern. The unique thing is a spatial pattern of the values, the attributes of those individual houses or households, okay? So various methods can be used to reveal whether similar values tend to occur near each other or whether high and low values are randomly distributed. So why do we measure the spatial pattern of feature values? We measure the spatial pattern of feature values because, quote, everything is related to everything else, but near things are more related than distant things. So what is that? If you've been a geographer for a while, you might have come across this statement. The idea there comes from Waldo Tobler, who's a fairly well-known geographer. He's actually passed in the last few years, and I believe he was at he was a faculty at UC Santa Barbara. And what this statement is known as is the first law of geography. So the key thing there is that near things are more related than distant things. So it's sort of the connection of not just spatial location, but quantitative or qualitative values about those features on the landscape. So let's kind of think about this a little bit more. So look at these maps here on the right-hand side. We've got a mean annual total precipitation map of the contiguous US. We have a map of the island of Honshu, Japan. And then we have the most popular female names in the year 2012. So it's interesting here, if you look at the first map, you can see that in the south, right, the southeastern United States, we have a high amount of precipitation. You move a little bit to the west through the Great Plains, that precipitation tends to drop. You look through the Mountain West, low precipitation. You look in the Pacific Northwest, high precipitation. So you see these bands, these color bands essentially across the United States. And you notice that not only are these areas close together, they also have a similar attribute. In that case, it'd be precipitation. So areas that are near each other tend to be related to each other. In that map of Honshu, Japan, you can see that mountains, those are the brown colors, tend to be close to each other. Those browns represent mountains, right? So mountains, landscapes, the landscape tends to cluster together. We have open plains to the east there. We have mountains to the west, the central, and we have probably hills around those. So topographical features tend to cluster together. And from a more qualitative standpoint here, we have names. And you can see in 2012, if you lived in the western United States or the Southwest, odds are your daughter was named Sophia. If you lived in the Midwest, your daughter was probably named Emma, based off of these common names. If you wanted a unique name, you had to either live in Vermont or Florida, apparently. So Ava in Vermont, Isabella in Florida. So, and Olivia and Emma, I didn't see that. Olivia in Idaho and Emma in Alaska. So at any rate, just notice that there are these spatial correlations of features that tend to not just correlate spatially, but also quantitatively or qualitatively in the values that they represent. So statisticians call this phenomenon spatial autocorrelation. In that case, spatial data exhibits autocorrelation when values measured nearby in space are more similar than values measured farther apart from each other. This also applies to temporal data as well. So when it comes to phenomena that occur in time, things that happen close to each other in time also tend to be more similar. And the best way to think about that would be the map there of the 2012 most common female name. And the best way to really understand that is to look at this map here. And this might be a little bit difficult to see on your screens. Hopefully you're watching this in high def. But we call this when features are close together in time, we call them serial autocorrelation. Okay, so it has to do with time. Serial has to do with time. So in the upper left-hand corner, we have a map of the most common female names in 1910. Okay, and you can see that most women, including my grandmother, who was born in 1920, were named Mary. Okay, so Mary was a common name in 1910, 1920. You start to see some Bettys in the 30s, right? So I'm not sure how old Betty White is, but I think she's as old or almost as old as my grandma. 1940s, we start to see some Sharons up in the Northwest, interestingly enough. A couple of Patricias there in the Northeast and in Oregon, Nevada. And then the 50s come, everybody's named Linda, right? So we see this massive Lindas come on the scene. Linda and still some Marys hanging about. There's the return of Mary in 1960, interestingly enough. You know, one generation skipped, and then, I don't know, parents want to name their daughters after themselves. I don't really know what's going on there. So we see this interesting influx of Lindas rather in the 50s, the return of the Marys in the 60s, and then the 70s come. We see sort of I guess you could see a regionalization in a sense. We see a lot of Jennifers. In the South, we see quite a few Angelas and Kimberlys. And then we move to the 1980s, and we see Jennifers. And then actually the most common name in 1985 was Jessica. And you start to see that show up here on the 1990 map. So we see Jessicas, we see Ashleys, and we see Brittany's. Moving into the 2000s, we see the rise of the Hannahs and the Emilys, right? 2010, we see lots of Emmas and Isabels. If you think back to this map right here, you had Sophia, Emma, and Isabella. Let's look on this map here. Where's Sophia's in black? So interestingly, a lot in 2010, Sophia hadn't quite picked up. So it wasn't until a couple of years later. Most of the girls there were named Isabella or Emma or you got some Madisons. At any rate, 2017, the most recent data I have on this map here. We've got Avas in the southeast. We see a spattering of Emmas and Evelyns and Olivias throughout the Midwest and the West. And then in the Northeast, in Maine, New Hampshire, and Rhode Island, we see Charlotte. So at any rate, it's just kind of a fun little thing to think about. But this whole concept of features clumped together in time tend to be more similar. And this is a great way to envision that. All right, so finding patterns, areas with categories. Areas with categorical data or categories can be measured using what we call join count statistics. So this is how we actually measure these patterns when it comes to categorical data. And I'll remind you what categorical data is in a moment. So areas with categories can be measured using join count statistics, which is used with contiguous, also known as adjacent, areas having category attributes. Category attributes are known as nominal data. Think back to week 2. Week 2, we talked about various levels of measurement: nominal, ordinal, interval, and ratio. So nominal data, also known as categorical data, are data that are qualitative in nature, meaning they describe something, but there's no sort of ranked progression. There's not like small, medium, large, first, second, third, and there's certainly no quantitative aspect to it. So you can't add nominal values together, and you can't rank nominal values. Okay, so one example I tend to use when I talk about this in my intro to GIS classes, if you've got a whole bunch of female names, for example, they're qualitative, right? But you can then turn those nominal names into ordinal if you alphabetize. Okay, so if we have Charlotte, Deborah, and Elizabeth, those on their own don't have any sort of rank value. But if you alphabetize those names, then you go from high to low, and then they do have an ordinal value in that sense. Okay, so nominal data are mutually exclusive qualitative data that cannot be ordered and have no intrinsic value. Examples of category attributes include land use types like residential, commercial, or industrial residential homes, commercial properties, or industrial property. Rock types like igneous, sedimentary, or metamorphic. So these are categorical data, meaning they are qualitative, and they can be divided up into groups. They can be grouped together, okay? So they don't have any sort of intrinsic value, no rank order, but they can be grouped. So within igneous, we'll have all sorts of like lava rocks and things like that. Sedimentary are rocks that have to do like sandstone and things like that. And then metamorphic are rocks that metamorphize and change over time. Residential, that could be single family homes, apartments, condominiums. Commercial could be strip malls, story high-rise structures, things like that. Main Street, Seal Beach. Industrial could be large factories, small factories, fishing, ports, things like that. So there are all these various categories that can be grouped together into residential, commercial, or industrial, or rocks of igneous, sedimentary, and metamorphic. So the GIS finds all shared borders, joins, they join together, join counts, between areas, and counts the number of these for which the value on either side of the border is the same and the number for which the values are different. The number of joins of each type is compared with the expected number based on the probability of two adjacent areas having the same value by chance. So again, this goes back to what we talked about last week. It's taking actual observed values and comparing it to random chance, okay? And then that above or below the random chance tells you if features are clustered or dispersed, okay? So if the counted numbers of joins for areas having the same value is greater than expected, the value is clustered. If it's lower than expected compared to a random distribution, it is dispersed. All right, so finding patterns in continuous values. Continuous values tend to be quantitative. Interval and ratio data are measured several different ways. Interval data are quantitative, that is numerical data, with a meaningful difference between values. Ratio data have the same qualities as interval plus a clearly defined zero. Okay, so examples of interval and ratio, percentages of population age 65 and over in each block group, elevation change over a 10-mile hike, and temperature readings across the state of California. The main thing to think about is not necessarily the difference between interval and ratio. It's just to point out that these are quantitative data, and in the context of finding patterns, we look at these as continuous values, and that they change from location to location. Areas with interval or ratio values can be measured several different ways. Examples for measurement methods that I'm going to discuss are Gary's C, Moran's I, and General G. And I'll explain what all these are. They've got kind of fun names. Without any context, they seem kind of silly. So Gary's C uses the difference in values between two neighboring features, developed by a geographer named Robert Gary and termed Gary's continuity ratio. That C stands for continuity. So it's Gary's continuity ratio. Statisticians and geographers just call it Gary's C. If the difference in values of nearby features is less than the difference in values among all features, the values are likely clustered. So what it does is it looks at the distance across all the various features in a data set and looks at the difference in values between any two neighboring. Okay, so it gets an average for the difference, the distance from any two neighboring features, and then if any two neighboring features are closer than the average of all distances between two features, those values are clustered. If they're greater than, then it's dispersed. So really, you find out what the average distance is, and then you measure a case-by-case pair, and if the pair is closer, it's clustered. So this indicates whether similar values are clustered, but does not indicate whether the clusters are composed of high or low values. If you want that, you're going to have to do something different. So Moran's I does not compare the attribute values for neighboring features directly to each other, but compares the values for each feature in a pair to the mean value for the data set. This is developed by Patrick Moran and termed Moran's index, Moran's I. Like Gary's C, if the difference in the values of nearby features is less than the difference in values among all features, like values are clustered together. This indicates whether similar values are clustered, but again, this does not indicate whether the clusters are composed of high or low values. In order to do that, you need to use a different method, which I will momentarily explain. The Geddes-Ord General G method measures within a specified distance how high or low the values are and compares this to the measure of how high or low the values are over the entire area. So what it does is it gets an average value for the entire study area, and then it finds clusters, and if they are above the mean or below the mean, those are considered really hot spots or cold spots. Okay, so what Geddes-Ord General G does is it tells you if there are any hot spots or cold spots, but it does not tell you both. Okay, so that's something to keep in mind. If you're trying to do a hotspot analysis, you need to use a different method, which I will be discussing next week. Okay, So the Geddes Ord general G method is developed by two geographers, Art Geddes and Keith Ord, termed general G because it calculates a single statistic for the entire study area. So it's general, so for the whole area. And it indicates whether high or low values are clustered, but it does not work in both directions, only for the highs or the lows. And unlike Gary's C and Rand's I, the general statistic indicates a general G statistic rather indicates whether high or low values are concentrated. So it tells you if there are clusters of high or low values. So as per usual, I try to include the little chart to explain what the method is, the data type that, or I should say that the level of measurement that these methods are applied to, what it will indicate, the benefits of this method, and the trade-offs. And I will not read through all of them because it's really just kind of rehashing what I just went over, but this might be useful for you if you are looking for measurement methods for your projects. So why identify spatial clusters? So we're moving into spatial clustering, which will be relevant to this week's lab a bit more. So why identify spatial clusters? Clusters occur when features are found in close proximity or when groups of features with similarly high or low values are close together. As I've mentioned just a little while ago, we look at clusters both in terms of spatial location and an attribute value. So think of the neighborhood, right? So all homes might be evenly distributed. So they're not clustered, they're not dispersed, but certain like attributes like median household income or house value or something like that tend to cluster together. And these are known as hotspots and cold spots. So identifying whether and where clusters exist is useful for targeting areas in need of particular focus. So if you're a geographer, maybe you're a city planner or some sort of an engineer, you might want to know where clusters are occurring because it allows you to focus your attention on areas of high need, right? So what are areas that might need a particular focus? Areas of high crime, for example, high crime neighborhoods. So if you want to look at the whole city of Los Angeles and you want to zero in on the areas with the highest crime, you might look for crime hotspots, right? And if you see crime cold spots, you know that you don't necessarily have to spend as much policing or resources on those areas because the numbers are already below average. Fishing beds and hunting grounds, so areas where natural resources are exploited from the natural environment. If you are looking for where are the largest clusters of fish or whatever, I don't know, hunting, we don't really, most food is factory farmed now, but we'll say that, 100 years ago or 200 years ago, you might want to know where the best hunting grounds are. So you'd use your proto-GIS to figure out where that would be. And so again, you look for where the clusters are, and that's where you will focus your attention. Customer bases. So if you are perhaps a market analyst and you're trying to find out where the best location is for a new Starbucks, you might have various criteria that you're looking for. People who like coffee, first of all, people who have cars and can go through a drive-through, people who have maybe disposable income, things like that, right? So you want to look for hotspots, clusters of these criteria, and then maybe you overlay those various hotspots and you can target the best customer base. Likewise, it should be high and low, not low and low. Sorry, high and low. I'll fix that in the lecture slides. High and low health outcomes. So looking for areas with below average health outcomes, maybe high mortality rate. Those areas would need additional focus for federal resources, right? And high and low income. Again, same idea. Areas of particularly low income might need additional school funding or things like that, right? So public resources. So by comparing locations of clusters to other features, by comparing locations of clusters to other features, it allows you to identify potential contributing factors. So knowing where clusters are, it's not just to tell you what the data are. It also allows you to look for other variables, contributing variables that might lead to some higher or lower value. So my example here would be comparing clusters of Ebola patients to environmental and economic data. So the possible spatial relationships between cases of Ebola and external factors may arise in the data. That map here on the right would be from the 2014 Ebola outbreak. Actually, started I think in December of 2013, and was the biggest Ebola outbreak, I believe, in recorded history. And so the question is, were there any sort of external factors that contributed to this rise of Ebola? Well, that's a question you have to ask. And so there actually has been research on that. And this is a map that it's real difficult to understand without all the context, but here on the right-hand side, you've got a timeline. The first outbreak in 1972, most recent 2014. And then you can see what were the animals that likely came into contact with humans to pass on Ebola, because Ebola is a zoonotic. I believe zoonotic is the term. Someone can correct me if need be. A zoonotic disease, right? It comes from humans, just like COVID-19 or the novel coronavirus, from animals to humans. And so, if we look at the countries where these Ebola outbreaks took place, we can also see the mortality rate on the bottom right, and we can see what animals might have had contact with humans. So we'll say, let's see, where's the most recent one? 2013 to present. So this is obviously a few years old. It was a bat. Once again, the bat, right? Jeez. So 54% mortality rate, terrible. Likely vector was a bat. In DR Congo, we see obviously previous outbreaks, not totally sure what the vector animal was. Back in the 1970s, it might have been a monkey or a certain kind of deer. Any other unique ones here? Congo, gorilla potentially. And so a lot of these are animals that were eaten. So I call it bushmeat, right? So animals that were eaten that were already infected with the disease, and then they're passed on to humans. So at any rate, just know that when you look at clusters of, in this case, clusters of Ebola virus, you're looking at, imagine a GIS taking another layer, a contributing factor layer, and so overlaying other factors like animals with a prevalence of disease. So that's really kind of the meat and potatoes of GIS. It's looking at correlations and correspondence between some feature on one layer and some feature on another layer. You don't really have to, this just goes with the previous map. I won't spend any time on it, but you can see the reservoir refers to the source of the virus. So using statistics to identify clusters. While conclusions about where clusters occur can be drawn by looking at a map, like we just did, significance testing allows us to test and validate those conclusions by measuring whether features are closer than would occur by chance. And if they occur by chance, that's what we call the null hypothesis, right? So if all things are equal, this is what it would be, and that's the null hypothesis. It's when the results differ, either in terms of being higher or lower than random chance, when something becomes significant. So spatial statistics and significance testing takes the guesswork out of identifying clusters. So you might look at a map and you might think you see a cluster, but you might be missing a cluster as well, especially when it comes to multiple events taking place on the same location, right? So if there are multiple events in the same single location, clusters can be hard to visually identify. That's why we need the statistics. Example I have here would be like imagine 6 robberies of the same 7-Eleven in a 1-year period. If you were to look at points, if one point represented one robbery, they'd all be stacked on top of each other. And so visually it'd look like just one single point. But if you do spatial statistics, you see that every single point represents an individual occurrence. So clusters can be formed 2 ways, as I've already talked about, by physical location of features or by physical location and attribute values. Clusters based on location alone are composed of what we call discrete features. Those are individual occurrences. Okay, individual occurrences. Discrete features may be points, like the example I just gave of 7-Elevens, or polygons. So that might be, something like an aggregation of features to a like census tract level or zip code level, right? So clustering tools look at the centroid of a polygon. So clustering results for polygons can be misleading, especially if the polygon is elongated or irregularly shaped. So something to keep in mind: if you have data that have been aggregated to a polygon, be careful if you convert those to points to do a cluster analysis, because the centroid of a polygon is not always within the polygon. A centroid may actually be outside of a polygon if it isn't oddly shaped. Like imagine a polygon that's shaped like a C. Well, where's the center of a C? It's not within the C, it's actually in the hole, right? Formed by the C. So clusters of features with similar attributes can be discrete features, points or polygons, or what we call spatially continuous data, and that would be quantitative data, right? And those are generally continuous data are visualized as rasters. So attributes for spatially continuous data are interval or ratio, as I have discussed. Finding clusters of features. So when finding clusters of features without regard to feature value, so just the physical location of the feature, we use a tool called nearest neighbor hierarchical clustering. Okay, you specify the distance features can be from each other, and then the minimum number of features that can make up a cluster. So there are various parameters that you have to input before you can run these tools. The nearest neighbor hierarchical clustering tool uses the distance between features, similar to nearest neighbor index like you used last week. It's hierarchical. We use the term hierarchical in this case because after delineating the first group of clusters, the routine continues on to group small clusters into bigger clusters, and those clusters into even bigger clusters. And you can see an example of that here. So we have individual occurrences are these little pink dots or orange dots. And then those orange dots can be grouped into small clusters indicated by the blue circles. Those blue circle clusters can then be aggregated into even bigger clusters indicated by the green hash mark or dotted lines here. And then those medium-sized clusters can then be aggregated into even larger clusters indicated by this large pink boundary here. Okay, so in this case, it would be a cluster of clusters of clusters. So 3 levels in this hierarchy, which can be visualized like this. So at the lowest level, we have individual incidents, actual occurrences. We'll say maybe robberies, right, of 7-Elevens or whatever. Then those can be grouped into first-order clusters. First-order clusters aggregated into second-order clusters, second into third, third into fourth. All right, so that's the best way to visually understand the nearest neighbor hierarchical clustering method. For nearest neighbor hierarchical clustering, we'll just call it NNH, the GIS uses a specified probability level to calculate the distance within which features will be considered a cluster. So you have to specify the probability that features will be within a certain distance are actually related to one another and not present by random distribution. So with a lower probability, more features will be included in the cluster, but the certainty that the features actually represent a cluster will be lower. So essentially you end up with a higher margin of error, even though you end up with a larger number of features within that cluster. A higher probability indicates fewer features will be included, but the certainty level will be higher. The confidence interval is the range within which the distance between 2 features may occur owing simply to chance. Okay. So we have a confidence interval. It's going to have a high and a low value. If the probability falls within that range, then that tells you it's most likely occurring to chance rather. Okay. If features are closer together than the low end of the confidence, so they're outside of the lowest level of confidence, then they are likely clustered together. If they are farther apart than the highest level of that interval, they are likely dispersed. Okay, so basically it gives you a range. Within that range, probably random distribution. Outside of that range, high probability that it is either dispersed or clustered. Finally, finding clusters of similar value. So to find clusters of features with similar values, the GIS looks at the attribute values of each feature and its neighbors, as well as proximity of features to one another, so distance to one another. The GIS calculates the degree to which nearby features have similar values for a given attribute, and statistical significance tests are run to determine the likelihood that a feature having values similar to its neighbors is not due to random chance. Methods for finding clusters of features within similar attributes are adaptations of methods discussed previously. For example, Gary C. and Moran's I, but are focused locally on a neighborhood. So Gary C. and Moran's I, if you remember, those refer to the entire study area. Okay, so that will be all the various features. When it comes to what we call local statistics, they're the same methods in terms of measuring the distance from one neighbor to the next and then comparing that to the average, but it works on a local neighborhood level. And if you think back to the definition of neighborhood in the context of statistics, that basically just refers to the area immediately surrounding a target feature. Okay, so these methods are termed local statistics compared to a non-local pattern finding known as global statistics. So Gary C. and Moran's I can both be used locally or globally. If it's global, it refers to the entire study area. If it's local, it refers to neighborhoods around each individual occurrence. So global statistical methods calculate a single statistic that summarizes the pattern for the entire study area. Local statistical methods calculate a statistic for each feature based on its similarity to its neighbors. Local statistical methods of Gary C. and Moran's I use the same methods as the global statistics, but focus on the local neighborhoods, as I said. So local Gary C. compares the values of neighboring features in a study area by calculating the difference between them. If the difference in values of neighboring features is less than the difference in the values among all features, the values are likely clustered. For local Moran's I, it compares each value in the pair to the mean value, and again indicates whether similar values are clustered, but it does not indicate whether clusters are composed of high or low values. That would be the Geddes-Ord general G statistic in order to do that. Okay, so thus concludes this lecture. Go ahead and move on to the lab. And as I said, there will be no tutorial this week. It's going to be the same approach as last week. You're going to have the lab PDF and then also the supplemental instructions to go with it. Use them in tandem. Obviously follow the PDF, and then when it looks like, oh man, this is referring to ArcMap, refer to the supplemental instructions. And I pretty much adapted the entire lab into the supplemental instructions, but you might still want to use the original lab document because it has graphics and things like that. So at any rate, just get going on that. Let me know if you have any questions. Post on the discussion board, send me emails, whatever. I'll be there for you. So yes, have a good week. Good luck during week 10. Next thing you know, we'll be looking at finals. So make sure you're working on your projects, and like I said, I'm available for meetings if needed, okay? So have a good afternoon, evening, morning, whatever. Take care.